All right, this is Air Conditioning and Heat Pump Specialty 4. This is the last of the series in prepping for the NATE test for both AC and for heat pump. Heat pump components. We've talked in other modules about the air conditioning components and what they do. Heat pump components are almost exactly the same with a couple little exceptions. One exception being we have a reversing valve. And that reversing valve changes the flow of refrigerant between the indoor coil and the outdoor coil. Which brings me to the next point. We don't call them the condenser and the evaporator with heat pumps. We usually refer to them as the outdoor coil, because in the cooling mode it acts like the condenser coil, and in the heating mode it becomes the evaporator coil. We also have two metering devices instead of one. Now, I need to preface this a little bit. These are bypass type metering devices. In the cooling mode, let me pick up the pen here. In the cooling mode, refrigerant will bypass the outdoor metering device and go to the indoor metering device, just like a regular air conditioning system. In the heating mode, we bypass the indoor metering device and we meter from the device at the outdoor coil. Some older units had a single metering device. It was a biflow type metering device, and it would usually it was at the outdoor unit, and the liquid line going from the outdoor unit back to the indoor unit was actually low pressure. I believe it was Westinghouse had it, and there may have been a few others. Like York might have had one model that did that. For the most part, though, you'll have two metering devices. Also, the indoor coil, again, just like the outdoor coil, it will act as the evaporator in the cooling mode. In the heating mode, it becomes the condenser coil. The other component we have is the accumulator. Now, the accumulator's sole purpose in life is to prevent liquid refrigerant from traveling back to the compressor. An accumulator is really nothing more than a steel can with a U-shaped tube in it for the inlet, and just dumping, a U-shaped tube in it for the outlet. I'm going to try to kind of sketch it off to the side here. The outlet tube looks something like this. This is the can of the accumulator. The inlet tube, this actually comes up more like this. The inlet tube just comes in like that. So refrigerant will dump into this accumulator, and it will be allowed to boil off. And as that refrigerant boils off, it enters the outlet tube here, which is shaped like a U, and then goes back to the compressor. At the bottom of this little U-shaped tube is an oil pickup. It's just a very, very small port, and it's there so that any oil traveling through the system will be allowed to go back into the return side, going to the compressor, and return that oil back to the compressor. Again, you have to imagine that it's just this deep, and disregard this other piece down here. Now, the way the refrigerant flows in cooling mode, it flows just like any air conditioning system. Hot gas leaves the compressor. In this case, it goes through a reversing valve and it's directed to the outdoor coil. The outdoor coil does like all condenser coils. It desuperheats the hot gas. It condenses it, and then it subcools it before it leaves the outdoor coil. When it leaves the outdoor coil, it's a high pressure liquid. It will bypass the outdoor metering device, travel to the indoor metering device, at which point the pressure's dropped, and it enters the coil as a low pressure, mostly liquid. When it goes through the metering device, you have a little bit of flash gas that drops the pressure and lowers the temperature, so it's a little bit of a mixture of liquid and flash gas. But as it goes through the indoor coil here, it evaporates, adds some additional heat as superheat, leaves the indoor coil as a low pressure superheated gas, goes to the reversing valve, is directed back down to the accumulator. From the accumulator, it goes back to the compressor. In the heating mode, things flip over. The reversing valve changes position so that the hot gas is directed to the indoor coil, and it acts as a condenser. It desuperheats the refrigerant, condenses the refrigerant, and then subcools it. And this time, instead of ejecting the heat to the outdoor air, we're ejecting the heat into the house. It leaves the indoor coil as a high pressure liquid, bypasses the indoor metering device, still goes through the liquid line as a liquid, is metered at the outdoor metering device to the outdoor coil. The outdoor coil is going to be about 25 degrees or so colder than the outside air, so it can pick up some heat. So it will meter the refrigerant into the outdoor coil. It picks up heat from the air going across it, becomes a superheated low pressure gas, goes back through the metering device, back to the accumulator, and then back to the compressor. Now, the accumulator, as I said, its sole purpose in life is to prevent liquid refrigerant from making it back to the compressor. When you have a heat pump operating in the heating mode, as I said a moment ago, this coil out here has to be at least 25 degrees colder than the outside air. And plus, as it gets colder outside, that coil gets even colder. We do tend to build up frost on the outdoor coil. It will frost up and ice up. As that ice builds up, that reduces the airflow across the coil, and it causes even more frost to build up. So roughly every 90 minutes, and it's adjustable between 30 minutes, 50 minutes, and 90 minutes, but roughly every 90 minutes, the system will go into a defrost cycle. In defrost, the reversing valve here goes back to the cooling position. So we're moving hot gas. Let me change colors of the pen here. We're moving hot gas into the outdoor coil. The outdoor fan is off, and that's causing that coil to heat up and melt that frost that's accumulated. Now, when this switch occurs, we've got hot gas and going into one coil, we switch positions, it goes into the other coil, and as this refrigerant's radically changing direction, there's a chance that liquid refrigerant from one of the coils will dump back into the accumulator, and that's what it's for. It's a place for that liquid refrigerant to go to evaporate before it goes back to the compressor. Now, the other thing that the accumulator does is it compensates for a change in charge. In a heat pump system, the charge needed for cooling is slightly different than the charge needed for heating, and there's about a 15% difference. So in the heating mode, there may be a situation where you get some liquid refrigerant going back to the accumulator, and the accumulator acts as a storage device, allowing that refrigerant to boil off. So again, there's about a 15% difference in the charge between cooling and heating. All right. The other thing we have to keep in mind about heat pumps is on the service ports. Here we have the normal service ports. I probably shouldn't draw it up like that, but we have the normal service ports right here. And in the air conditioning mode, we can connect our gauges up to that. That's fine. It will work perfectly well. However, in the heating mode, things are a little bit different. In the heating mode, both of these lines, the liquid and the vapor line, become high pressure lines. Now, in our drawing here in the middle, you can see the hot gas goes down through the reversing valve, and then that hot gas goes through the vapor line to the outdoor coil. This is no longer a suction line, it's a vapor line. That pressure can either be low pressure during cooling or high pressure during heating, and the pressure on the liquid line and vapor line will be really pretty close to each other. So both of those are high pressure in the heating mode. If you make a mistake and put your gauges on these particular ports in the heating mode, if you have the analog type gauge, your low side gauge may be damaged because you're going to run high pressure to it. Most heat pumps have a third port, and this third port, which is right here, that third port is connected between the accumulator and the compressor. So it's between this point and this point, and it's always low pressure. So when you're on a heat pump system and you may be in the air conditioning mode, you'll want to connect to the liquid line service port like you normally would, but then you'd also want to connect to the low side port, which is usually through the cabinet like this. Now, this is usually like this. Some of these ports are directly on the line between the accumulator and the compressor. They don't extend outside the cabinet. You have to kind of look. Different makes have different setups. The other thing you want to remember, when you work with a system that's set up like this line coming off this low side pressure port is usually a capillary tube. It's a very small line, and it's just there to give you pressure. So if you go to evacuate a system and you connect your low side port to this, it may take a little bit longer to evacuate because you're trying to pull it through, in essence, a capillary tube. And in that case, you'd want to go back to the vapor line port right here because it's a larger line. It's easier to pull your vacuum that way. All right, that's a little bit of how the difference between a heat pump system operates for the flow of refrigerant from an air conditioner. Let's talk about some of the different terms that we're going to see on the test. First one I want to talk about is energy efficiency ratio. It used to be the main form of efficiency rating for air conditioners. They've since changed it. We're all aware that it's SEER now. But the energy efficiency ratio is the ratio of cooling effect per hour divided by the power consumed in watts per hour. Now, you still see this rating. You'll see it on window units and you'll see it on geothermal systems. The reported EER, in other words, the EER that they put on the tag to that window unit or that geothermal unit, is based on that unit's performance. In other words, its cooling effect compared to the power it's used when the system is at 95 degrees outside temperature and 80 degrees, 67 degrees wet bulb temperature inside. So it's going to be 80 degrees dry bulb, 67 wet bulb. That's going to be all indoor conditions, and 95 degree dry bulb outdoor conditions. So that's the reported EER. Seasonal energy efficiency rating, or SEER, or SEER rating, that's the one we're most familiar with. It's a measure of the cooling effect of an air conditioning unit or a heat pump, and it takes into account the starting and stopping and the variations in temperature that occur over the cooling season. It's still a reasonably, it is a reasonably good measure of how efficient a system is. When they do a SEER rating for a single speed system, and this is a unit that has a single speed compressor with a fixed single speed outdoor fan motor, they do the test at 82 degrees Fahrenheit outdoor temperatures with an indoor temperature of 80 degrees at 67 degrees wet bulb. And that's the reported for the single stage. Two-stage units and variable speed units are a little bit different. They do the reported SEER ratings for those based on tests using 8 what they call bin temperatures. And there it is. Because the system doesn't operate at 82 degrees all the time outside, they do 8 different temperature ratings. And the ranges go from like 65 to 69, 70 to 74, 75, 79, etc. And they call that bin temperature, the average bin temperature is 67, 72, 77, etc., all the way down. And they weight those readings. So they'll take the measurement at 67 bin, and they'll find out what the EER is there, and then they'll do the same thing at 72, 77, and so forth. Then they weight that, and they weight it by the percentage of hours that you stay at each individual set of temperatures. So, 21% of the total SEER rating is going to be based on what occurs at 67 degrees, and 23% is going to occur at 72 degrees, and so on. Because when they report this, they're using temperatures that don't typically go up into the hundreds. They use a very small percentage to affect that. So they take these numbers, they average them all together based on these percentages, and that's how they get the reported SEER rating for variable speed equipment or multi-stage equipment. By the way, you may want realize it goes down to 65. 65 seems really cool, but 65 degrees is the temperature at which we start cooling degree days. So 65 degrees and above, there is the potential to have cooling on. Another term, and this one's used mostly in heat pumps, is called coefficient of performance. It is the ratio of BTUs in heat produced by the amount of power is consumed. It's very similar to EER, except the watts consumed are multiplied by the heat content of the watts converted to BTUs. So really what COP is, and the easiest way to understand it, it's how much heat you're getting for the amount of power you're using. Now, if you were to take 2,930 watts and you applied 2,930 watts to electric heating elements, you would take 2,930 times 3.413, and that gives you 10,000 BTUs. However, when we work with a heat pump and COP, we would take the same 2,930 watts, and if we applied that power to a heat pump with a coefficient of performance of 3, the heat output would be 30,000 BTUs. It would be 2,930 times 3.413 times 3. So if you want to look at it like this, a heat pump is 3 with a COP of 3 is 3 times as efficient as a straight electric heat, or you could say 300% efficient for straight electric heat. Now, the number that we're most familiar with when it comes to heat pumps is called HSPF, or Heating Seasonal Performance Factor. And it takes into account, because COP, the coefficient of performance, varies based on outdoor temperature, the HSPF takes into account various temperatures. It's very similar to the SEER rating, and it checks or averages the performance at 47 degrees Fahrenheit and at 17 degrees Fahrenheit. And they use those two ratings, and that determines what your HSPF number is. Basically, it's designed to be the total heat output for an entire season divided by the total power consumption in that equipment for the same season. Now, EER, you can actually measure EER. We actually used to do it to check the performance of a piece of equipment. First step to doing this is to measure your airflow. Now, you can measure airflow using the external static pressure, evaporator pressure drop, temperature rise method, or velocity. It doesn't matter, but you have to physically calculate the amount of airflow going through the system. You cannot say, well, it's a 2-ton system, it's going to have 800 CFM. That doesn't work. You have to actually calculate it for the formula to work. Now you're going to use a psychrometer. And you're going to take that psychrometer and measure the wet bulb temperature entering the evaporator coil, the indoor coil. And then you're going to take the wet bulb temperature leaving the indoor coil. Once you have those two wet bulbs, you're going to use a psychrometric chart or an app on your phone to convert that to BTUs per pound of air. And that's going to give you enthalpy. So and enthalpy is represented by the letter H. So you're going to get H1 and H2 out of the entering wet bulb and the leaving wet bulb temperature. After that, we're going to determine the wattage of both the indoor and the outdoor units. To determine wattage, it's volts times amps equals watts. And then we're going to use this formula. H1 minus H2 times CFM times 4.5. That's going to give us our BTU input. And we're going to divide that by the condensing unit watts, or the outdoor unit watts, from the indoor unit watts. That will give us EER. 4.5 is a conversion number. It converts CFM to pounds per hour. All right, so let's go through an example here. So we measure 1068 CFM. We've gone through and used the different methods to do it. We got our entering wet bulb temperature at 67 degrees. We looked on a psychrometric chart, and it says that 67 degrees wet bulb is equal to 31.93 BTUs per pound of air. The leaving wet bulb temperature is 58, which equals 25.1 BTUs per pound of air. The condenser power is, or the outdoor unit power is 2332.8. The indoor unit's power is 511.7. And we start plugging those numbers into the formula. So what we come up with is 31.93 minus 25.4 times the CFM, which was 1068 times 4.5. That gives us 31,383 BTUs. The watts from the indoor and the outdoor units are 2332.8 plus 511.7. That gives us 2844.5. You divide 383 by 2844.5, and that gives you 11.03 EER. When it comes to calculating COP, this is usually done to determine how much heat the heat pump is producing in relationship to the power that it's consuming. You're going to measure the airflow just like we talked before. You're going to use a digital thermometer. Here we're not getting wet bulb temperature, we're getting dry bulb temperature. We're going to measure the dry bulb temperature entering the indoor coil and the dry bulb temperature leaving the indoor coil. Next, we're going to calculate wattage of the outdoor unit and the indoor units. Wattage is volts times amp. Now this time we have to be absolutely sure that we don't have any electric elements cycling on, because we're just trying to find out the heat output of the heat pump, not the electric elements. So we start plugging these numbers in. We'll take our temperature rise times 1.08. 1.08 is a conversion factor for the weight of air. 1 cubic foot of air equals 0.0, it's actually 0.0755. Everybody rounds it to 0.08. Then our CFM, that equals our BTU output. And then we're going to take BTU output times the watts times 3.413, and that's going to give us our coefficient of performance. So if we measure 1228 CFM in this particular heat pump, and we get the entering temperature of 67, the leaving temperature of 93, we find out that our outdoor unit has 2405 watts, the air handler has 1094 watts, and we have a temperature rise of 26 degrees, and we figure out that we have an input of 34,482.24 BTUs. That's how much heat is being produced by the heat pump. So we're going to plug it into the formula, 34,482. We're going to take our total watts, the 2405 right there, plus the 1094 there. That will give us 3,500.2 times 3.413. We divide that together, and right now under these conditions the heat pump is operating at a coefficient of performance of 2.89. So for every watt of power that I produce in there or put into the heat pump, it is producing 2.89 times the amount of heat that I would have gotten if I put that same amount of power into an electric strip. Or you can look at it like it's 289% more efficient than straight electric heat under these conditions. All right, that covers some of the formulas, some of the terminology. Let's talk installation practices. And these are not in any particular order. In fact, they're a little out of order, but that's fine. The installation practices, the detail within each practice we've talked about in other modules, but we want to talk about how we go about putting it together here. The air conditioning practice and heat pump practice are essentially the same. The first thing we need to talk about is clearances. The main thing we need to keep in mind on clearance is the side of the unit that has the control panel where we actually have to service the unit. You have to have at least 30 inches to that side of the equipment. To the coils, the coil inlet, you have to maintain at least 12 inches. So you can't put it any closer than 12 inches to a wall or some other obstruction. If you have multiple units, you have to maintain at least 24 inches between the coils of those two units because they're both drawing air in. You have to basically double the inlet coil clearance to make sure you've got enough airflow going through the coils. Okay, the system should be mounted onto a slab. The slab can be either completely level, which would be appropriate for air conditioning, or it can have a 2-degree pitch away from the building. Now that's for heat pumps, and the reason we do that is when a heat pump defrosts, all that frost that was on the coil melts and runs down to the bottom and out the drain holes in the base pan. When that hits the pad, it needs to flow away from the building. You don't want water puddling up next to the foundation of a house. It'll get into the house. It'll also cause the ground to settle differently, and the heat pump will start to pitch, and you'll get some erosion underneath the slab itself. So you want to have it pitched 2 degrees away. Now the great way to figure out 2 degrees pitch is it is a 2-inch drop for every 5 feet. So if you have a 5 feet piece of wood, it should be 2 inches lower on one side than the other. That gives you your 2-degree pitch. Heat pumps, air conditioners are not an issue here, but heat pumps need to be placed or can be placed on either a stand or a lift if there is heavy snowfall. And the rule is that whatever your average snow level is on the ground, let's say you have snowfall of 6 inches, and that's usually what stays on the ground, you need to elevate your heat pump 6 inches above the average amount of snow, average snow accumulation. So if I had typically 6 or 8 inches of snow on the ground throughout the year, I would want to have a 12-inch stand or 12-inch pump up to raise the heat pump above that level of snow. This will allow the drains to drain properly and keep from obstructing the outdoor coil with snow piling up to it. Other installation practices, brazing refrigerant lines. We've talked about brazing in other modules. Obviously, we need to cut our tubing and make sure it's deburred. When we're installing equipment, though, we're usually doing the brazing at the service valves, at the outdoor unit, and sometimes on the valves at the indoor coil, depending on how it's set up. When we run into this situation, we need to remove the Schrader valve cores. Now that's the little piece inside the valve itself that you depress. It's like on your bicycle tire. Those have rubber rings to them and rubber seats, and if you heat those up too much, they won't seal any longer. So you need to use a tool, something like this, to get in there and remove that core. And the cool thing about this tool is I can put it on, use this lever here, or this knob, to unscrew the core bring it back into this area right here, this valve here shuts it off, so it basically shuts off this part of it. And I can replace the core if I need to, but it also allows me to have a completely open service port right there without the core being in place. This greatly reduces evacuation time. It's really hard to pull a lot of refrigerant around those cores, or a lot of either air or refrigerant, whatever you're trying to evacuate from the system, from around those cores. You take the core out, it goes much, much faster. You should always attach a nitrogen tank with a regulator to your gauge ports through your manifold gauge set. And this is to purge the lines with nitrogen before you start doing any brazing. The idea here is I want to displace the oxygen. Oxygen and copper together, when you heat it up, forms copper oxide, which is a black flaky like material, and it will plug metering devices and screens and things like that. If we can avoid it, it makes for a much better system. And the way we avoid it is to use nitrogen. We'll pass some nitrogen through it, allow the nitrogen to flow through the system while we're brazing the fittings. Also, there are seats in a lot of the service valves. Those seats are usually made out of nylon, and if you overheat the nylon while you're brazing a fitting, it will leak and you won't be able to use the valve to shut the system back down again or do a pump down. Also, the packing around the stems can be damaged, and it can cause it to leak around the stem of the service valve. When you put your nitrogen on, you want to maintain a very low pressure, usually 1 to 2 psi-G. This is enough flow through the line sets to displace the oxygen. You don't want to put a lot of pressure there. If you put a lot of pressure on this, what will happen is as you're trying to braze, nitrogen's trying to escape around the fittings, and it will make it difficult to make a good joint when you braze. Okay, installing metering devices. This doesn't apply as, it's pretty straightforward doing a piston type or fixed metering device, and you do have fixed metering devices on both heat pumps and air conditioners. But if you're installing a expansion valve, it's a little more complex. The sensing bulb, if the line is 7/8 inch or less, should be installed at the 12 o'clock position. Now, it says at the 12 o'clock position in various code books. Manufacturers will say anywhere between 9 o'clock and 3 o'clock, and those will be fine. If the line is larger than 7/8 of an inch, you're supposed to put it at the 4 o'clock or 8 o'clock positions. And there's images of the two differences. When it comes to leak testing the system, pressurize the system using nitrogen. You are limited to the pressure that you put into the system to the test pressure of the weakest part of the system, which is typically the evaporator coil. If the evaporator coil has a test pressure of 150 psi, that's the maximum test pressure that you're going to use. If you don't know what the test pressure is in the system, always go back to 150 psi. That's going to be your default setting, so to speak. Once you've leak tested the system, you're confident that you don't have any leaks, it's time to evacuate. If you're dealing with all new equipment, you can do one deep vacuum and you're fine. This is if you have new line sets and coils and outdoor units and things like that. If you are reusing components from the previous system, in other words, you're reusing line sets or coils or something, let's say you're going out to replace just the outdoor unit, we don't know if there's any moisture in those other components, and in those cases what we need to do is triple evacuate the system to make sure there's no moisture left over. When it comes to power wiring, your equipment wire size, the wire actually feeding the equipment itself, needs to be sized based on the minimum circuit ampacity on the rating plate of the unit. That's how you size your wires. There also has to be a disconnect installed. Technically, according to code, the disconnect has to be within sight of the equipment. Personally, I would rather have it within arm's reach. so it can be easily accessed without having to, you know, run over 50 feet to get to the disconnect. Thermostats, and this is a little point of contention, and I think they're going to pull the thermostat questions out of the test. Technically, thermostats should be mounted 5 feet above the floor, 60 inches. But there's the ADA requirements, and that means that Americans with disability you have to lower that. You have to have wider doorways and things like that. But also, in many cases, you have to have lower sinks and lower things like thermostats. So, in certain cases, the American Disabilities Act requires that you have the thermostat set at a lower level. Because of that, I think they're going to remove these questions out of the test. I don't know if they've done that yet. So if you see a question at what's the proper height for a thermostat to be set, it is still 60 inches or 5 feet. And it will be until they start pulling those out. The other thing about thermostats will be the position of the thermostat so it's not affected by sunlight or drafts. Ground wires. All pieces of equipment must have ground wires installed. When it comes to condensate lines need to have a 1/4 inch per foot pitch away from the unit. 1/4 inch per foot. When you terminate that condensate line into a drain, either a floor drain or some other type of drain, you need to maintain a 1-inch air gap. And that's there so that if the drainage system should back up, you don't get that backup into the condensate line. The secondary pan has to be used on any indoor unit if it's installed above a living space. The secondary pan must have a separate drain to it or have some means to disable the equipment like a float switch. Where there is a secondary drain, that drain has to be piped separate from the primary drain, and it has to be piped to a conspicuous location. Okay, that covers our installation things, the thing that I think will come up on the test. Let's talk a little bit about service practices. Whenever you go to service a unit, now there's a lot of discussion at NATE about what happens first, and if you got 15 people in the room, you'll have 15 different opinions. So it's really pretty limited to checking the wire, but not the order at which you check the wire. So you can check your wiring system, check for the cleanliness of the outdoor fan, motor, and blade. Now when they talk about the fan motor, what they're looking at is, unless it's a sealed motor, there are eyelets in the motor itself to allow for ventilation, airflow to go through there to keep the motor cool. If you get a situation where there's a lot of dust and dirt built up in those, your motor can overheat. So part of the practice is check it for cleanliness and clean it. You should also check your blade. And the main thing I want to check for the blade, not so much cleanliness, because blades frankly don't get that dirty, it's for cracks. Because if a crack develops in the blade, it will continue to get worse and worse as that blade flexes when it runs. The crack will get worse, and when it reaches the edge of the blade, it can cause that blade to peel up when when the fan's running. Now when this happens, any wires in the way will be destroyed. It will throw the balance of the blade off. It will cause a lot of vibration. It can actually cause that fan blade to pull out or tear away enough to damage the outdoor coil. So look for cracks. If there's significant cracks in the fan blade, you need to replace the fan blade. The base pan, we need to check the drain ports in the base pan for any kind of debris and clean them as necessary. The base pan is the bottom of the outdoor unit. It's the thing that the outdoor coil sits on, the compressor sits in, and things like that. That's called the base pan. All of them have little drain ports so that when it rains, water doesn't build up in there, and when it freezes in the wintertime, We need to keep those ports clean, because if you do get water that freezes in that area, you can damage the fins of a coil. Also, it can cause corrosion and things of that nature. You should inspect the condition of the refrigerant piping. Make sure those pipes are not rubbing copper to copper within the unit. That will cause rub-through leaks. You should also make sure that your wiring is not touching your copper tubing, because as that copper tubing vibrates inside a unit, it will literally vibrate through the insulation, and you can get a short that way. You want to check the condition of the insulation on the refrigerant lines. Now, insulation on refrigerant lines has two purposes. One is to prevent condensate. When you run this line through an attic or across a living space or something like that, if the insulation is damaged and ambient air can contact that vapor line, it can condense and leak and cause water spots along ceilings and things like that. The other reason to have it is so that the system doesn't pick up excess heat. So if I have a vapor line running through an attic and the insulation's damaged, I'm picking up all the heat from the attic, and that's using part of the capacity of the system, and it's lowering the capacity that actually is used to cool the space. So those are the two purposes of insulation. That's why we need to check the insulation on the refrigerant lines. Always do a capacitor check. Inspect the contactors for pitting and burn marks. We should also look for worn fan motor bearings. Now, these are the fan bearings in the outdoor unit. We'll do the same on the indoor unit. It'll come up in a couple of clicks. The way you check those bearings is you grasp the shaft. This again is with the power off, but you grasp the shaft and you try to move it perpendicular to the motor. If you get any movement perpendicular to the motor, the bearings in the motor are starting to fail. And you will feel it. It will be a rattly type feel when you try to move that shaft perpendicular to the motor. We also want to inspect and clean the outdoor coils. We're going to check all of our component wiring. We're going to clean and replace the air filters on the indoor coil. We're going to make sure the indoor blower is clean. The thing that you need to be aware of, if the indoor blower is dirty, the indoor coil is also dirty. I can almost guarantee that. So in addition to checking the air filters and the indoor blower, you need to be looking at the indoor coil. And if one of those is really dirty, the coil is probably dirty as well. We should inspect our coil drains and make sure that those pans are not cracked. Some of them were made out of steel to make sure they don't have a lot of rust or any kind of obstruction that could cause it to have a leak. Best way to confirm that your drain pans or your drain lines are working is to pour a couple liters of water into the pan and make sure it drains all the way to the outlet. And as I said a moment ago, be sure you clean that indoor coil. The other thing that you want to look at is the refrigerant lines between the indoor unit and the outdoor unit. And there's not a lot of damage that can happen to these lines. It's usually, when something does happen to these lines, it's catastrophic. Somebody drives a nail into the roof and it goes through and happens to hit a refrigerant line, and this can cause a catastrophic type failure where we have a really bad leak. But what you really want to do when you inspect refrigerant lines is look for signs of oil. Oil circulates through the system with the refrigerant. If there are leaks, you will see oil residue. Now, where you see the oil is not necessarily where the leak is. There are many cases where you have a leak at a fitting up in an attic and you notice the oil where it comes out at the bottom because it tracks along the pipe. But it's a good indicator that there's a leak, so you need to go back wherever you see the oil around a fitting, you need to check that fitting for leaks. You should also check the duct system. Now, leaks in duct systems rob capacity. If you've got a leak, an air leak in a duct in an attic, it's going to either pull in hot attic air or it's going to eject conditioned air into the attic space and not do the homeowner any good. The other thing you want to look at is crushed ductwork. Crushed ductwork, disconnected ductwork, things like that. So always inspect your ductwork, make sure it's in pretty good shape. Just like the outdoor coil, or I'm sorry, the outdoor motor, you want to check the indoor motor, check the bearings of those. Again, with the power off, try to move the shaft perpendicular to the motor. If you get that rattly feel, the bearings are wearing out, you need to replace the motor. And that completes it. That covers everything that you should need to prep for the AC and heat pump training.